Good morning, everyone. I'm Sobi Matthew, tech lead for ARM Trusted Firmware-A project. So today we'll describe the dynamic configuration feature as implemented in TFA. So we know of several use cases where this feature will be useful. For example, we had a couple of talks yesterday describing how device trees are used to configure different various software layers. And we know of several other use cases where having a device tree to be visible across different bootloader images is useful in general. So I'll be describing some common use cases. I also will explain the position-independent executable support as implemented in TFA. This is kind of related to dynamic configuration because now you can dynamically load your bootloader images without having to worry where the firmware images were compiled at. This is a quick recap on dynamic configuration. So we had a session in San Francisco at Connect 2017 where Dan Handley described the dynamic configuration as a BOF session. If you're, I guess most of you are already familiar with Trusted Firmware-A. The boot is split into several stages, and the first stage is known as BL1. The BL1 image starts executing from the secure ROM. The second stage, BL2, is loaded by BL1, and then BL2 is then responsible for loading all the subsequent bootloader images. So you have several bootloader images shown in the diagram. You have BL31, BL32, which is the trusted OS, for example, Opti. Then you have BL33. BL33 is the normal world bootloader, like U-boot, UEFI, and BL33 is responsible for loading the kernel along with the file system and the device tree blob. So this is the typical boot flow in Trusted Firmware-A. So what we've done is to add dynamic configuration, we've added small configuration files. If you see the white boxes over there, those are the configuration files which are getting passed along for each bootloader image. So if you look at BL2, there's a configuration file, tbfw-config, that's getting passed to it. Similarly, for BL31, you have the SOC firmware config. For BL32, you have the TOS firmware config. For the normal world bootloader, there is a NTFW config getting passed. The SW config is usually the Linux device tree. So the SW config can be made visible to all the bootloader stages. So it can make use of the information in the Linux device tree to configure the information, or maybe modify some change, make some changes to the Linux device tree blob. Yeah, so the block arrows show the load sequences. So BL1 is loading BL2, and BL2 is loading all the other bootloader images. And the thin arrows show the execute sequence in the diagram. So dynamic configuration is an optional feature. Platforms can choose to implement it. DTB is the format used for the config files on ARM reference platforms like FOSS models and the system guidance platforms. Some of the envisaged use cases are dynamic configuration of secure firmware features. Basically, the firmware can dynamically enable or disable some features based on the configuration described. Hardware configuration, security policies. Modification of hardware configuration is another case where a previous bootloader stage can make some additions or modify the configuration file for the later bootloader stages. It can be also used to pass information between bootloader stages. Currently, before dynamic configuration, if you needed to pass information, you need to either change the handover interface or you need to extend the ABI between the bootloader images. With dynamic configuration, you can just add it as a property in the dynamic configuration, and then you can pass that information. We'll see some example use cases later. Going on to some implementation details. So as as I mentioned, there was a session in SFO 17 regarding this, and most of the use cases as described in that session are, we have the necessary framework in place. Currently, none of the trusted OSs make use of the config files yet, but there is a plan to have at least opt-e enabled to use the configuration file going forward. So static firmware configuration was also described as a possible use case for this feature. But on implementing it, we realized static firmware configuration is better implemented with a config-driven build system like kconfig and keep dynamic configuration separate. As part of the implementation, what we've done is unified all the arguments that are being unified in the sense we have a fixed set of arguments that can be passed between BL images. So you can pass 4 registers as arguments now. Previously, we used to have a handoff interface. So in order to maintain compatibility, we've added the additional arguments around the previously existing handoff interface. So the dark blue boxes show the existing handoff interface without dynamic config. And the light blue boxes show the additional information that's getting passed. For example, if you take between BL1 and BL2, which is the first box shown over there, there are 3 arguments being passed. arg1 was the mandatory argument, which was the memory info from BL1 to BL2. Now 2 more arguments are added, arg0 and arg1, which point to tbfw config and hw config respectively. Between BL31 and BL33, there is no mandated handoff sequence as of now. What we've done is we've introduced a handoff sequence, but currently there is no ABI between BL31 and BL33. Every platform tends to use their own ABI. Perhaps in future it is good if an ABI can be evolved in the space, but we'll have to take this as we go forward. Just to give an idea about the configuration file, I've picked up an example from FEP. So this is the tbfw config in FEP platform. This is shared between BL1 and BL2. As you can see, there are properties describing where the hardware config is to be loaded, which is the Linux device tree. Then you have a property describing the authentication, disable authentication. So this authentication is a feature that is there when you enable trusted board boot. So now you have a property saying whether you want to enable it or disable it. I'll describe that in a slide later on. Then you have a couple of properties mentioning where the other config files are to be loaded. Another benefit we gained out of implementing dynamic configuration was the embed TLS, ability to share embed TLS heap. So when trusted board boot is enabled in trusted firmware, we use the embed TLS library for doing the crypto operations. And both BL1 and BL2 need to use embed TLS library. Before dynamic configuration, we had no way of sharing the heap between BL1 and BL2. Now, using dynamic configuration, BL1 passes its heap address to BL2, and BL2 uses the same heap as BL1 for embed TLS. So using this, we were able to save about 13 kilobytes of memory for FEP in BL2, which is quite a big savings in firmware terms, because your total SRAM may be like 128 kilobytes of memory. Just describe some typical use cases for this. As I mentioned previously, you can dynamically disable trusted board boot for development. What we've done is, if you build ARM TFA in the debug build, that's when you get this ability to dynamically disable. If you build it for release build, it's always enabled, so you don't get that capability. So what happens is, when trusted board boot is enabled, when you are developing firmware, it's quite difficult to change a firmware image because you have to change all the associated certificates up to the root of trust. So having a dynamic property to whether to enable or disable trusted board boot is useful, because while development you can disable it and you can keep updating your firmware images without worrying about certificates and all that bits. This is another use case where the kernel device tree can be loaded to an address which is described dynamically in tbfw config. Uh, the, the sequence is described in the slide. Basically, BL1 authenticates and loads tbfw config. BL2 then figures out where the kernel device tree blob is to be loaded. It loads it accordingly. BL33 has an argument pointing to the kernel device tree, and it needs to pass this information onto Linux. Similarly, other configurations are also are all loaded dynamically using the information in tbfw config. This is an extension of the previous use case. In addition to loading the kernel device tree, the bootloader images can make use of the information in the kernel device tree, like, for example, address of some certain peripherals described in there. Also, secure devices can be described in the hardware config, which are then used by all the bootloader images. It can be then removed, or if you are not worried about security, you can keep it there and then passed on to Linux. Linux will just ignore it. This is another use case where we've seen a lot of people asking for this. So when you have trusted OS and Linux communicating, you usually have a shared buffer between them. And the location of the shared buffer has to be communicated to Linux to use it. So typically, this is now communicated using custom SMCs. So this is one possible way where you can use dynamic configuration to share this information. You can have a property describing where the shared buffer is placed in memory, and then that can be populated into the Linux device tree, and then Linux device tree gets that information. Another variant of this is when the trusted OS is executing, it will create secure carve-outs in memory, and the secure carve-out memory has to be communicated to Linux so that Linux will not use it. Currently this is done manually in the sense that you have to make sure that your trusted OS and the device tree has to match, and it's done manually. So using dynamic configuration, trusted OS can directly modify the Linux device tree blob to add this information into it. Okay, so what dynamic configuration is and is not. All the dynamic configuration files are part of chain of trust, and they are authenticated as part of loading them to memory. Once they are loaded, they can be modified. Each bootloader stage can modify the configuration for the next bootloader stages. Conversely, later bootloader images cannot change the configuration for the earlier bootloader. Dynamic configuration via configuration is expected to be done only once during boot. So after the boot is over, if any further configuration is required, then you must use an SMC. The configuration memory used for these config files can be reclaimed once the information is consumed by the bootloader image. So now we'll move on to some details about position-independent executable. So as I mentioned previously, this is kind of related to dynamic configuration because now you can describe where the bootloader images can be loaded dynamically using a configuration file, and you don't have to worry where the firmware images were compiled to run at. So to enable position-independent executable, we had to enable a couple of build flags. Basically, you need to specify fpi and a couple of build flags to the compiler and the linker. So once you specify these build flags, additional sections will be created in your binary, which is shown in the block at the right-hand side. You need a loader to fix up these sections. So the approach we've taken in TFA is, instead of the loader fixing up these sections, each bootloader image does its own fix-up as part of beginning to execute. So in the dynamic sections shown in the block on the right-hand side, you have the most important ones we care about are the .got section. You can see the size also mentioned over there, all are in hexadecimal. Then the .dynamic section, which describe all the other dynamic sections in the binary. Then you have the .rela section, which has the dynamic relocations. We found that Pi adds about 5 kilobytes of memory to the binary on a FEP release build. So if you are really constrained on your platform, then this may not be an option for you. But it brings in a lot of flexibility for a developer. So we have to find the relevant sections for fixup, and the only sections that I found that needs fixing up are the .got and the .rela sections. It has to be done very early before the bootloader image starts running. One of the problems we have is the ELF information is stripped out of the binary images and then loaded. So at runtime, you don't have the ELF information anymore. So there are ways to get around this. For example, in the .dynamic section, you have a description of all the dynamic section in there. And there are some compiler symbols which export the start of some of the dynamic sections. So instead of doing all that, we did an easier implementation where we marked the beginning and the end of the section in the linker script. And we use those linker script defined variables for fixing up later on in code. So the global offset table fixup, I'll describe some details on it. So position-independent code in general cannot have absolute virtual addresses, right? So when you compile it for PIE support, all the absolute addresses are now placed in the global offset table, and then your code references the entries in the global offset table using relative addresses. So as part of the fixup, all the entries in the global offset table now has to be corrected based on the difference between your compile address and your run address. One thing that you need to be aware of is the assembly files don't generate GOT entries. So if you have assembly files in your code, it has to be fixed. You have to manually fix them up to remove all the absolute address references and change them to relative addressing. So an example is shown on the slide where an LDR instruction is changed to addrepy relative addressing. Be aware that addrepy shouldn't be used for constant values, because if you use addrepy for constants, then they are not constants anymore, they become relative. So next is the dynamic relocations, the fixup for the .rela section. Just some background on what relocations are. Relocations, probably you already know them. So relocations are entries in binaries that are left to be filled in later. So they can be filled in later by the linker statically or by the loader, which is the dynamic relocations. Typical examples for dynamic relocations are structures encapsulating callback functions. So at compile time, the compiler populates the address which is as per what the compile time addresses are. So during runtime, these callback functions, these function pointers have to be fixed up before they can be invoked. The dynamic relocations are in .rela sections. So if you look at the ELF64 specifications, there are several types of dynamic relocations. The idea is to control the number of types of dynamic relocation so that you can implement a simplistic and not so complicated or a small loader in the firmware. So we found that there is only one type you need to typically handle, which is the ARC64 relative type. There may be other types which may be created by the linker, but we found that it's due to some exotic code patterns in your code, and by changing the code, you can change that relocation type. I have some examples in the backup slide, so if you're interested, I can discuss it later on. So this is the data structure for the .rela section. You have three fields in there, offset, info, and addend. Offset is nothing but the address where the fixup needs to be done. Info is the type of relocation in our case, which is the ARC64 relative type. And addend is the address which is known at compile time, and then based on the difference between the compile and runtime address, you have to fix up the addend. So the fix-up is quite simple. You go to roffset, find the difference between compile and run address, and fix up the addend and write it to that address. Some limitations of the current fix-up code in TFA. The fix-up code assumes that the BL binary is a contiguous binary that is relocated as a single blob at runtime. So this is not the case for BL1. BL1, as you know, it starts executing from ROM. The text and the read-only sections are in ROM, and the data has to be copied to RAM at runtime. So it's a disjoint binary. So if you relocate a disjoint binary at runtime, because your code and read-only are remaining at the same address, all of the binary sections are not moving at the same relative offset. And there is no real use case for enabling Pi for BL1 because it is ROM code. Another limitation is because firmware is quite tight on memory, we tend to use memory carve-outs for storing data at runtime. So some of these carve-outs are created using linker scripts which fix an absolute address to that carve-out. So when you relocate your binary, these absolute carve-outs remain at the same location, whereas your binary moves. So as shown in the picture on the right-hand side, when you compile your address, your binary is now generating relative addresses to a data carve-out which is fixed in memory. And at runtime, when you move it, your binary also assumes that the carve-out has moved along with the binary, but now, which is not the case, so that goes wrong. So there are a couple of ways to solve this. One way is don't use linker script to fix absolute address to have data carve-outs. You can have a pointer and you can allocate it at runtime. Yeah, there are other ways to force the compiler to generate absolute addresses to these carve-out memory. The other limitation of the current implementation is this all ties into tight memory constraints in firmware. So we reclaim some of the initialization code at runtime, and there is a flag to enable this feature. This is similar to the underscore init attribute in Linux kernel, where once you load a driver, all your init sections can be reclaimed later on by the kernel. It's similar to that conceptually. So what we do is all the init sections are placed in a separate section, and then the firmware can choose to use it for data later on at runtime. On FEP, this section is used for secondary CPU stacks. So because this is a runtime overlay, it creates quite a complicated relocation entry in the dynamic relocation, and the current fixup code doesn't handle it. Okay, we think dynamic configuration is a very interesting feature because I've been having several discussions during the past week, and I've heard many people very interested in doing this, and there are several cases where this can be useful. For example, currently in the Linux device tree, you have the CPU nodes and the PSCI power state parameters, which are all hand-coded. And this has to match exactly with firmware for it to work. All of this can be made dynamic. So since firmware has this information, it can populate this information into the kernel device tree at runtime. I think dynamic configuration will unlock more opportunities to share memory between BL images and reduce the overall footprint. The final intention is if you have a set of related platforms which has similar but slightly different configuration, you can have a single firmware image and you can have different configuration files to describe it. And that single firmware image can now run on related platforms. The flip side is your memory footprint increases slightly because now you need to parse the device tree blob and you need to include the device tree library into your firmware binary. We need to have better adoption in partner platforms and trusted OS, because currently if you look at upstream trusted firmware, everybody is doing their own thing. If they need to use the device tree, every platform tends to do it in their own way. It's good to have some unified way of doing this dynamic configuration. That's all I had. Any questions or comments?
So I would like to get back to the dynamic configuration part. So first of all, the comments. So if you would actually show those snippet that you've shown on the slides here to your colleague Rob Herring, he would get icons because it violates all conventions for naming node names and property names. So please talk to each other. So doing underscores is an absolute no-no there. Yeah. Second, you were talking about using those device tree blobs to pass information from like an earlier stage to the next stage. And it seemed that you were using a new self-contained blob for that, and you were talking about the term Linux kernel DTB. Yeah. There is no such thing. There is the DTB. It is being currently hosted as part of the Linux kernel repositories, but it is not a property of the kernel. It's supposed to describe the hardware. Yeah. So that brings me to my final point. Why are you not simply reusing that existing blob by simply moving that out of the BL33 binary where it's currently being provided by UBIT, for example, or EDK2, making it as an additional entry in the FIB table so that you can access it from all your BL blobs?
Yeah, so the thing is, not all the configuration that are done between the bootloader images need to be exposed in the device tree blob. So sometimes the BL images can have private information just shared between them. And device tree blob is not, we are not mandating any format. It's just that if we find device tree is the most convenient format to use. So the platforms are free to choose their own format in the space. And we think that it's just more flexibility for platforms to define their own configuration file if they just want to limit it to the different bootloader stages and not expose it externally to the kernel, which is the device tree blob in there.
Yeah, just keep in mind that trusted firmware is not used on only Linux device tree-based systems. So
yeah.
It's the same case with the U-boot, basically. Yeah, when we add a device tree, we have maintained separate device tree blobs in U-boot, but at the end we maintain, we are reusing the same thing from the Linux. That's what I'm thinking, because if you have a common device tree, the binding becomes more easy for the user point of view, right?
Yeah, yeah. So but not all platforms, so not all the platforms that we care about use Linux or the Linux device tree blob. For example, you can have Windows platforms, and you can have ACPI-based platforms. So it's giving more flexibility to the platform. But you could choose to have. We are not mandating anything in this space. Okay. You could choose to put everything in your device tree blob and then pass it along.
Do you have a separate binding documentation for this configuration?
The binding is also platform specific. So whatever bindings I showed you, it's only a convention that's used within ARM platform layer, ARM reference platform layer. Okay. Other platforms in trusted firmware are free to choose their own bindings. Because one of the issue is because there are so many cases that can be handled, it's difficult to come up with standardized binding for all of those cases. Perhaps in future, once we see some commonalities, we can define more common bindings. But this is very early days, and we just want to give flexibility to the platforms.
Do you use a libfdt for unblobbing the tree?
Yes, yeah,
okay.
Yeah.
Okay, thanks.
Oh, yeah. So actually, it's more of a suggestion instead of a question. Would you consider adding a DTB overlay feature? So instead of requiring that the DTB that you want to add nodes to is in your FIP, define an address. It's just as an additional feature so that when you get to U-boot, you can merge it in, which is kind of what we did with Opti then and in MBL. It's worth thinking about, I think.
It can be done in the current scheme because all you need is a configuration file, and as far as the TFA generic code is concerned, that configuration is a black box. It doesn't care whether it's a device tree blob or it's overlay or it's some other format. It just passes on that information, and it's a black box for the generic code, and it's up to the platform to interpret that.
So all I'd say to there is maybe add it to your slide as here's another way you could do it.
Okay. Yeah.
Yeah. So.
Yeah.
So you mentioned that least there's the idea that you could modify those config files via an SMC call. Like if you wanted to make I think, wasn't there something you said where if you wanted to make a permanent modification to one, there was an SMC call, or did I misunderstand that?
So
or at least conceptually, an SMC call could be used to modify them?
No. So
okay.
what I meant is, because the dynamic configuration is a configuration that can be only consumed at boot time.
Right.
And then the files are no longer used. If you want to make further changes to your firmware, behavior of your firmware,
Okay,
or further configuration to your firmware,
got it.
you have to use an SMC.
I thought in the Trusted Firmware 2.1, Trusted Firmware was able to boot straight the Linux kernel as a BL33, not going through a non-secure bootloader before the boot.
Yeah.
And with the scheme you presented, the boot arguments are not compatible with the one expected from the Linux kernel.
Yes. So So if you look at the BL31 to BL33, the arg0 is currently default assigned to NTFW config, and arg1 is the HW config. If you flip it around, arg0, if it points to the Linux DTB, then you can boot Linux kernel directly from BL31.
Maybe I'm wrong, but I thought it was arg2 that carried the DTB. But maybe I'm wrong.
Yeah. So this is something that we can decide. If we think that there is a sensible way of putting, better way of arranging these arguments.
Well, if it could be harmonized whether this hardware config is used or not, still having the same boot arguments for the BLs, it would be more easy.
Sorry, I can't hear.
Sorry, it would be more easy if it would be the same boot argument for the several BLs, whether this dynamic configuration is used or not. Because you said it's an optional thing, this boot argument.
Yeah.
This hardware config, sorry.
Yeah. So, because not all the platforms are using any configuration, are using configuration files, we can't enable it by default. Only the platforms which have hardware config and using them, we could. So we can change the default implementation to have a layout which is compatible, so that you can boot kernel directly. We can change that. Yeah.
Just a clarification also. I think you mentioned that what you present is what ATF does. Is it what it does as of today with the 2.1 that is released, or is it what you plan to release in the next one?
You mean the use cases or the arguments?
Not the use cases, because that's platforms that decide whether.
So,
but yes, these arguments and all this scheme and those.
So that is as done in 2.1 release. Yeah, it's there presently. Yeah.
Okay, thanks.
I have a question about the PIE, right? PIE feature. What's the difference between the PIE and the KASLR, kernel address space randomization?
Those are two different concepts, I think, because PIE is allowing your binary to be independent of the, you don't need to worry where you run it later on. You can load it anywhere in memory and start executing it. Whereas the kernel address space randomization is every time you boot your kernel, you have a different mapping of virtual addresses.
By the MMU?
Yeah. So that's a different.
So the PIE don't need the MMU feature. Well, I mean, if I disable MMU in ATF, the PIE also can be configured and run, right?
Sorry, I didn't get your question.
I mean, if I disable the MMU in the trust firmware, so the PIE can be running, can run, okay.
You mean if you disable MMU, whether PIE will work or not?
Yeah.
It should work, yeah, because all the relocations, as long as they are fixed up, it should work, yeah.
It's just by the fixed address.
Sorry?
I mean, if you means if you disable the MMU, so the PIE feature just runs by fixed address, right? Or like
So the PIE doesn't rely on the MMU to work. It's more like the code is actually fixed up based on your runtime address. So your code is, your code is modified at runtime. Your actual reference. So I can show an example. So this is an example of a GOT entry fixup. Okay. Yeah. So for example, you have a print over there, BL31 version string. So that's a string literal which is usually encoded using absolute address over there. So during when we do the fixup based on your run address, this is fixed up to point to the correct address before the code starts running. So yeah.
I got it. Thank you.
Trusted firmware runs with identity methods anyway.
Yes. So usually the physical and virtual addresses are same in trusted firmware, but you could have them different, but yeah.
A follow-up to the question from the gentleman in the back. So when we're thinking about executing the kernel as a BL33, do you have any provisions how to deal with PIE as far as the kernel is concerned? Because today, the DTB structures at least often have, like a fixed address that describes at which location in memory the ATF blobs need to be reserved. And obviously, if they, based on some config files that they get from BL2 or somewhere else, move around in memory, then that information would need to be relayed to later boot stages as well. So either, for example, if it's U-boot in BL33, then U-boot would need to be made able to actually parse those config structures that you try to pass to them here via the dynamic configuration. And of course, it would need to be then passed on from U-boot also to Linux or whatever the exact payload is.
So when you relocate your BL images, you have to be careful that you don't overwrite or you don't touch any of currently the config files are put in a separate partition in the RAM. So when even though with PIE you move your BL images around, the information in the config files still stay relevant, right? Because as far as the currently populated information in
I mean, the key point here is with PIE is that you can load the same blob at different addresses. So it could be, at 0x1 with lots of zeros, or it could be at 0x2 with lots of zeros. And you need to reserve that memory also within the final guess that is running in the memory. It needs to be aware that it should not touch that memory. That's what I was talking about.
Yeah,
and you need to get that information
yeah.
to that particular instance.
Yeah. So usually the firmware runs in a secure memory, which is not at all visible to kernel at all. The problem happens when if you're running out of DDR, which is usually available to the kernel, and you create a secure carve-out in there. That's when all this information now has to be passed to the kernel. Yes, I agree. So if you are having a different address where you're creating your carve-out and you create it dynamically, your DTB blob has to be modified to reflect that information to kernel.
I think that is where the question from the gentleman over here also comes into play. So is the vision that for a given platform, despite PIE, you would still always have it at a fixed address that could be hard-coded at the U-boot or Linux layer? Or do you expect that to be, like dynamically moving around in memory like the KSLR?
No, we don't expect that much dynamism because, first of all, we don't have too much memory available. The primary use case is to enable PIE is if you compile a firmware image for a particular platform and you have a related, slightly related platform which has a different memory layout, you can use that same firmware image to run on the other platform. It's not like you would want to keep relocating your BL image within the same platform. So you compile one firmware image with PIE, you can execute it on another related platform. It may have a different memory map, so you can run it with the same firmware image. You don't have to worry whether the addresses match.
So Sobi, one kind of really simple solution is, instead of having a DTB file that you input when you're creating the FIP, is just generate a DTB in memory. So you can put your GOT anywhere and then just modify a DTB that you create. So I'm not sure what the licensing on it would be, but in opti and U-boot, I believe, libftd is imported. So maybe a stripped down version could be done for TFA. Or
yeah, so it's a perfectly legal case. It's just that if you are to create it in memory, I guess
I keep suggesting you do more work here.
Yeah. Yeah, so there are many ways to do this, yeah. We don't limit anything.
Yeah, sorry, I will come back in something we already discussed, but just to point it out and share with other people. Is this a hardware configuration board? With this scheme, the hardware configuration board is used both by the secure bootloader and the non-secure boot stages.
Yeah.
And so it is bound to some secure keys. And there might be some time when you have some hardware and you plug some extension boards, things like this, that are used by the non-secure board. Mm-hmm. So you change the hardware config, but maybe you still do not have access to the secure key. So you won't be able to regenerate the hardware configuration because you don't have the key for it.
Right.
Just, I don't know if it's a real issue, but just wondering if it should be considered.
Yeah, we need to think how we would handle that, yeah.
And no, there is this non-secure configurations, firmware configuration thing where maybe this could learn, but it's still hardware configuration things that should be changed. So yeah. All those device trees are bound to authentication keys, which are bound to security domains, and
yes.
It makes things less flexible, actually.
Yeah. So you have a different, so that's why if there are limitations on generating the keys, another option is you can use an overlay, just like what is done for ARC32. ARC32, you generate the overlay, and then U-boot can combine it later on. Other way is you give that information as a NTFW config to U-boot, and then U-boot can then merge it into the Linux device tree.
Yeah, I agree. It would be a way to tackle that, yes.
Yeah. Okay. If there's nothing else, thank you, everyone. Thanks for attending.